Welcome back to the lectures in Introduction to Multi-Agent Systems. In the previous lecture, we talked about the Laplacian flow solutions. We also introduced some of the properties associated with the exponential of the negative of the Laplacian matrix. That particular matrix has several other interesting properties as well, which we will discuss in today's lecture. Let's get started. Before we actually continue our discussion on the Laplacian exponential, we'll first introduce yet another matrix, which is derived out of the Laplacian matrix and has some nice properties. We will be using this new matrix to actually arrive at more interesting properties associated with the Laplacian exponential. So let's get started. We'll in fact start with an example. Let us consider the diagraph that is shown here. For this particular diagraph, we know that Laplacian is equal to the out degree matrix minus the adjacency matrix. So let me directly write what it's going to look like. The out degree of first node is 1, and it has an outgoing edge to node number 2. Hence, I can directly write the entry like this. Node number 2 similarly has just one outgoing edge to node number 1. Node number 3 has outgoing edges to every other node in the network. Node number 4 again has an outgoing edge only to node number 1. So this is a Laplacian matrix. What is equal to L max here? Now just to remind you, we had defined L max as a maximum over all of the diagonal entries. In this case, L11, L22, L33, and L44. So the diagonal entries are 1, 1, 3, and 1. Hence, L max here directly is equal to 3. Let us now construct a new matrix. Let's write it. This is L max. Using L max, we define a new matrix as follows. Our new matrix is, we call it AL. It's equal to L max times the identity minus the Laplacian. So what does this matrix evaluate to for the diagraph that is shown to us? Let's see. For us, L max, as we know, is 3. So it's multiplied with identity. So we get a diagonal matrix with all entries equal to 3. And Laplacian is as shown here. This is a Laplacian. When we subtract the two, what we get is, so before we write it, let's look at the construct a little bit. We see here that all of the off-diagonal entries of a Laplacian are always non-positive, meaning when we subtract it, all of the off-diagonal entries of AL will always be non-negative. And what will happen to the diagonal entries? The diagonal entries again will always be non-negative. The reason being that it will be equal to 0 for that particular row which has the diagonal entry equal to L max. But for every other row, it's going to be a positive number. So in this case, what we have is AL is equal to 2, 1, 0, 0, 1, 2, 0, 0, 1, 1, 0, 1, and plus 1, 0, 0, 2. So this is what AL looks like. Notice here a few things. Okay. Let us now, we will highlight a few interesting properties associated with AL. Let us construct a digraph using AL as the adjacency matrix. Call it GAL. And again, obviously, it will have 4 nodes. Let us draw the nodes first. So I've drawn the nodes here. This is GAL. Now let's look at the adjacency, AL. So node number 1 has a self loop of weight 2, and it also has an edge to node number 2. Node number 2 now again has an edge to node number 1 and also has a self loop of weight 2. Node number 3 similarly, again, much like the previous digraph, has edges to every other node. And node number 4 again has an edge to node number 1 and also has a self loop. Weight of the self loop is equal to 2. Let us look at the original digraph, which was G of A, and let's see what it looks like. Let me simply copy this digraph and place it right next to our new graph. These are the 2 digraphs that we have. This is G of A. What do we observe? We observe that the nodes which were adjacent here continue to be adjacent in GAL as well. We just have the addition of self loops. Otherwise, every other edge that is there in GA is still there in GAL. Meaning, what can we say about GAL? We can say the following. We can say that for AL defined as L max IN minus the Laplacian, G of A and G of AL have the same set of edges other than the self loops. The self loops is yet another property. Additionally, AL is a non-negative matrix. We are already familiar with a lot of nice properties that we can associate with the adjacency matrix when it is a non-negative matrix. So what have we effectively done? We started with the Laplacian for a given digraph. Using this Laplacian, we constructed a new matrix AL. The new matrix AL that we have, it represents yet another digraph, but this digraph, the new digraph, is exactly the same as the original digraph with the addition of a few self loops. Additionally, the adjacency matrix for this digraph is a non-negative matrix. With this, we are now ready to state the third property of the matrix, the Laplacian exponential. We have discussed the first 2 properties in the previous lectures, and now we'll start with the third property. So let's write it. Properties of Laplacian exponential continued. The first property goes this way, or rather the third property. It says that e to the power minus L is greater than or equal to e to the power minus L max times In, which is now greater than or equal to 0. So this 0 is a matrix, n cross n matrix without zeros. Okay, the proof of this is quite straightforward when we use our newly defined matrix AL. Let's see, how does it go? Let us consider the previously defined adjacency, or let's write previously defined modified adjacency matrix given by AL equals L max times In minus Laplacian L. From this, it follows that minus of L is equal to AL minus L max times In. So we will focus our attention on this expression now. Let us consider the exponential minus L, that is e raised to the power minus L. We can substitute this expression here to get exponential of AL minus L max times In. So what can we write this as? So it is the exponential of a summation of two terms. So hence we can express it as the product of the individual exponential of both of the terms. Meaning this is e raised to the power AL times e raised to the power minus L max times In. So what does this evaluate to? This evaluates to e raised to the power minus L max into In is equal to, so again we can write a power series expansion here and write In minus L max In plus minus L max whole squared times In squared. Let's write it. Minus L max In squared divided by 2 factorial plus so on and so forth. This becomes equal to times In. What we can write here is In minus L max times In. Now In squared is nothing but In again. Hence, we can write this as minus L max squared times In. Again, for every other term with higher powers, In to the power k is simply equal to In. So we can take out the In and write it separately here. What can we do next? We can further take In common. And what are we left with? We are left with 1 minus L max plus L max squared divided by 2 factorial and so on and so forth. Hence, e raised to the power minus L max times In is actually equal to Let's look at this term. What is this equal to? This is simply equal to e raised to the power minus L max. Hence, this is e raised to the power minus L max times In. Notice that we first substituted this. Let's write it. So this is e raised to the power minus L max. And notice here that this is a scalar. Hence, what we did is in the next expression, we simply brought it here. And what remains is an n cross n matrix. Okay, now let us plug this expression in our original equation that we have here. E raised to the power minus L is equal to e to the power Al times e to the power minus L max In. That now becomes equal to, then e raised to the power minus Il, which is e raised to the power Al minus L max In is equal to, again, e raised to the power Al times e raised to the power minus L max In. This is equal to e raised to the power A alpha into or multiplied by e raised to the power minus L max, which is now a scalar, times In. Hence, we can ignore the In, it's just an identity matrix. Hence, what we have is e raised to the power minus L now can be simplified to e to the power minus L max, which is nothing but a scalar, times e raised to the power A alpha. What is e raised to the power A alpha? Notice that, okay, let's simplify it a bit more. We can further simplify and write it in this manner. This is equal to e raised to the power minus alpha, minus L max, times, now let's do a power series expansion of the second term. I plus Al plus Al squared 2 factorial, and so on. Hence, what we can do is, we can multiply L max with all of these terms. And if we ignore all of the higher order terms here, then what we are left with is e raised to the power minus L is actually less than or equal to e raised to the power minus L max times In. In this expression, we have simply ignored all of these terms. Hence, if we delete all of these terms, now this is what we get, which proves our third property. Let's look at the third property again. This is exactly what the third property said. E raised to the power minus L is greater than or equal to e raised to the power minus L max times In. Let's see the expression. Sorry, there's a typo here. This should be greater than. Why should it be greater than? Please take a note of this, or let me write this part again. This can be simplified as L max times In plus rest of the terms. If I ignore the rest of the terms, what I get is, obviously, e raised to the power minus L is now greater than e to the power minus L max times In. And since all of the entries, e raised to the power minus L max is a positive number, when multiplied with identity, we get a matrix which is obviously non-negative, as given here, which proves the third property. Let's now look at the fourth property, which is now a slightly more topological or graph theoretic property. So what does this property say? Fourth property actually says that the jth column of e raised to the power minus L is positive if node j of the given digraph G is globally reachable. This is the third property. It says that all we need to do is look at the exponential of the Laplacian of negative of the Laplacian. And then we look at the jth column of this exponential. If this jth column turns out to be positive, then the jth node is actually a globally reachable node. So we knew some similar properties in the sense of the adjacency. However, now we are actually looking at the exponential of negative of the Laplacian and now trying to derive properties out of this. So how does this follow? How can we make this claim? Let's look at the proof of this. Again, the proof follows quite directly from the new Laplacian matrix that we have. Let's see how it goes. Sorry, the new adjacency matrix AL that we have. Let's start with the proof. We know that, or let's start with this. Consider the digraphs G A, which is the original diagram, and G of AL, where AL is again the same adjacency matrix given by L max times IN minus of. Okay. What do we know about them? Again, we saw it before. We know that GA and GAL have the same set of edges, except obviously the self loops. Right. So what does this imply? This implies the following. When the jth node of GAL is globally reachable, then the jth node of G of A is also globally reachable. This is an important property. That means, can we now show that if e raised to the power minus L, somehow if its jth column is all positive, then correspondingly these two things hold. And when is the jth node of GAL globally reachable? So this is also something again which we studied before. So let me write a recap here. This is something that we have discussed before. We know that the jth node of GAL is globally reachable if the following holds. That's right. Let's highlight it in a different color. If the jth column of the summation k raised to the power 0 to n minus 1 AL raised to the power k is positive. So now we started by saying that, let's say the jth node of GAL is actually globally reachable. Then what will have this property holds. The jth column of this entire summation of matrices is positive. What happens then? How does this relate to the Laplacian exponential? Let's see. Again, e raised to the power minus L, as we saw in the previous proof, is equal to e to the power minus L max times e raised to the power AL. So the proof of this we discussed earlier in this video. And what we can again do is we can write e raised to the power minus L max times I plus AL plus AL squared up to infinity, meaning e to the power minus L is equal to e to the power minus L max times the summation of k going from 0 to infinity, AL raised to the power k. Obviously, this is greater than or equal to e raised to the power minus L times the summation going from k raised to the power 0 to n minus 1. If the jth node is globally reachable, then the jth column of this summation is positive. Since e to the power minus L is actually greater than or equal to this, what can we now say? We can say that, notice here that all of the entries of e raised to the power minus L are positive. Hence, by multiplying e raised to the power minus L to this summation, it cannot make any of the positive entries here equal to 0. Hence, whatever entries are positive, after multiplying e raised to the power minus L max, obviously the entries remain positive. Meaning, what we can say with certainty is that this would directly imply that the jth column of e raised to the power minus L is also positive. What did we show? We showed that if e raised to the power if j is globally reachable, then eventually it turns out that the jth column of e raised to the power minus L has all entries which are positive. Yet another property which follows quite directly from the fourth property. Imagine that the network is strongly connected. What happens then? In a strongly connected network, every node is in fact globally reachable. Hence, every column of e raised to the power minus L is now positive, meaning the fifth property follows quite directly. The fifth property says is e raised to the power minus L is positive if G is strongly connected. We will skip the proof of this as it follows quite directly from the proof of the fourth property. With this, we end today's lecture. In the next lecture, we'll try to see how exactly can we use these properties to actually comment on the stability of the system and whether or not we achieve consensus using the Laplacian flows. Thank you.